So today we're very pleased to have another theorist with us, Daniel Stolarski. So Daniel, if my Googling skills are correct me if I'm wrong, did his PhD at UC Berkeley before going on to postdocs at Johns Hopkins, Maryland, and then CERN, and finally joined Carleton as a faculty member in 2016. So today Daniel is going to tell us about emerging jets and promises to make it accessible for all of us non-collider people. So let's aim for like 45 minutes so that we have some time for questions, if that's all right.
Sure.
Take it away.
All right. Yeah, thank you, Aaron, for the introduction and for the invitation to come speak. That was the correct history. And yes, the goal is definitely to make it accessible to non-collider people. But certainly please interrupt me and stop me if you have any questions. I'm happy to take questions in the middle. I'm not sure I can see the chat, so shout out over the microphone, or Aaron can shout out if there's questions. So I'm gonna talk about so around this paper from a few years ago, but also, if I have time at the end, a bunch of work that's related to that that is ongoing with my group at Carleton. So let's see. Okay, so let's start with pi. I always want to start a talk with pi, and the cosmic pi in particular, which is that the energy budget of the universe, we can go out and measure the entire energy of the universe. And it turns out that only 5%, so can people see my mouse?
Yep.
Okay, yeah, only 5%, this little orange wedge of the pie, a very meager slice, is stuff that we actually understand. So the periodic table and the standard model of particle physics and all those things, all of that is this tiny wedge of the cosmic pie, of the total energy of the universe. And so we do not understand 95% of the universe. This biggest slice is dark energy, which I'm not going to talk about today. It's an interesting story, but it's not what I'm here to talk about. So first, I want to talk about this very healthy and delicious looking slice of dark matter, which is about a quarter of the energy density of the universe, and notably much, much bigger than this slice of atoms that we understand. So dark matter, we have very good evidence for dark matter. And probably you've all seen talks about dark matter, so I won't spend a lot of time going over the evidence, but just quickly, let me talk about 3 pieces of evidence for dark matter. The first is the rotational galactic rotation curves. So if you look at how fast the stars in the galaxy are spinning about the center of the galaxy, and then you do the calculation that you can do in first-year physics using Newtonian mechanics of how fast they should be spinning, this is the red curve, and the actual measurement is the white curve. So there's a huge difference between these two. And one way to explain this is if the galaxies have more mass than we can actually see, if there's some additional dark mass or dark matter in these galaxies, which provides additional gravity to keep these stars from flying away. The second one is observations of the bullet cluster. So this is a collision of 2 clusters of galaxies, not just galaxies, but many, many galaxies clustered together. And the red in this image is the visible stuff you can see with your eye or with an ordinary telescope. And the blue is the total mass of the galaxy that's measured through what's called gravitational lensing. And you can see that there's a displacement. So when these 2 galaxy clusters collide, the gases interacted with one another and they get dragged, but there's this collisionless dark matter which gets separated and it just passes right through one another. So you get a displacement between the red and the blue. And then the most convincing piece, and the one where we can really quantitatively get that pi on the first slide, is from the cosmic microwave background. On the other hand, that's the most difficult to explain, so I won't talk about it too much here. But this is the photons that we see that come from the early universe, the very, very early universe, the first 100,000 or so years, when the universe was about 100,000 years old. You can take that picture, and that's this thing on the left, and then roughly do a Fourier transform of that picture. And the dots are the data, the red dots are the data, while the lines are what you get with different amounts of dark matter, where you can see that the error bars on this data is very, very small, and only with dark matter being about 25% of the universe do you even remotely agree with this data. For example, this dotted line of no dark matter is very, very far away from the data itself. So, okay, I'm going to take dark matter as a given. And so now we want to go out and search for dark matter. And there's a very rich experimental program to search for dark matter. There are many, many different experiments searching for many kinds of dark matter. So this one experiment is the Deep 3600 experiment, which is physically located at Snow Lab in Sudbury, Ontario, and has many Canadian collaborators working on it, including people at Queen's and at Carleton. And so these kinds of experiments, they search for dark matter, and mostly they search for what's called a weakly interacting massive particle, or a WIMP. And thus far, this experiment and many, many others, what they've done is said what dark matter isn't. So that's an interesting statement, but it's not as interesting as if they told us what dark matter is. So here's some pictures saying that if dark matter had certain parameters, we would have discovered it already, and because we didn't, it can't be there. And there's various different experiments. So I've just shown plots from Deep 3600, the Canadian one, Super CDMS, which also has Canadian collaborators, and I think people at Queen's working on it, gives a different set of limits. But so far, all these experiments have given limits. Another possibility is to try to make dark matter. And so the one way to do that is at a particle collider. So the Large Hadron Collider is the most famous and highest energy of these colliders. And here's a picture, or a picture of where the collider is. It's actually underground, but this is the Swiss-French border. And you can see on the right side is the Geneva airport. So this is an enormous ring that's 100 meters underground and collides protons at extremely, extremely high energies. And so quantum mechanics tells you that if it's possible, it should happen. And it could happen that these collisions of protons will make dark matter. And if so, well, how do you find it? And you find it with a detector. So something that's basically taking pictures of these proton collisions. So this is a giant detector called the Atlas experiment. You can see it's a little blurry in this photo, but there's a person here. The detector is here. So it's much, much larger than the length of a person. And there are many Canadians working on the Atlas experiment as well, including people at Carleton. And so this is an enormous project, and it's one of the most complicated scientific pieces of equipment ever built. And it measures the results of these proton collisions. And so far, it hasn't found dark matter either. It places limits on various WIMP-like models. So this weakly interacting massive particle, there are very strong limits coming from colliders, which are complementary to the limits from experiments like Deep 3600. Okay, so that's the dark matter slice of the cosmic pie. Let me go back to this thin slice of atoms of the part that we do understand. So actually, we don't totally understand it. Because what we see of these atoms is all matter and no antimatter, roughly, to a very good approximation. And the reason that happened, what we do know about it, is that at the very early universe, for every 10 million quarks or baryons or protons or however you want to think about it, for every 10 billion quarks, you had, for every 10 billion antiquarks, you had 10 billion plus 1 quarks. So there had to be more matter than antimatter, but only at the 1 part in 10 billion level in the early universe. And then all the antimatter annihilated with all the matter, and you have this the 1 bit in 10 billion is all that's left. And everything we see in the universe today, all the atoms, all the stars, all the planets, all the people, all came from this one tiny excess of matter over antimatter. And so we know this had to happen, but we don't know how it happened. So there has to be some physics that caused this asymmetry to happen. And we know that has had to happen to match the observation of our universe being here and not being empty. But it's not really that well understood why it happened or how it happened. And then there's one more slice of the cosmic pie, but it's so small that you can't see it, which is light, right? So starlight and light from the cosmic microwave background and all the photons, all the light in the universe. That makes a piece of the pie, which is 1/1000th the size of the piece for atoms, right? So I didn't put it on the plot because it would be invisible, But there is this light piece, which light is also something we understand. We have a nice theory of electromagnetism that we understand very well. But there's only a tiny, tiny amount of energy in the universe in light. And the lesson from this is that, well, we know roughly in the very early universe, we had the same amount of atoms as light. But the evolution of the universe and just doing simple calculations in statistical mechanics tells you that you end up with way, way more atoms than you end up with photons. And this is generically true. If you write down some model of particle physics and then you do the calculations from fourth year statistical mechanics, you end up with orders of magnitude differences in the energy density of the two species. Of course, you can imagine that they end up the same. So, for example, the energy density in protons and in neutrons is very similar. But that's because the protons and the neutrons have very similar properties. They have almost the exact same mass, and they have the same strong interactions. And so it's not so surprising then that you get similar energy densities. But when when the two species are very different, like photons and protons, for example, you get very, very different. Generically, you get very, very different energy densities in the universe. And yet, if we compare the size of the dark matter slice and the ordinary matter slice, well, they're not the same. And if you got the ordinary pi versus the dark matter pi, it's a big difference, but they're the same order of magnitude. There's only a factor of 5 difference, right? And if you write down a random model, you should expect to see that they're orders of magnitude different, especially since, as far as we know, the dark matter is not the matter. It can't be exactly the matter, and it's maybe not at all similar to the matter. So why should these two numbers be the same order of magnitude, only a factor of 5 difference? And the usual WIMP models that people have studied, they don't really explain this fact. There's no connection in those models between the energy density of atoms and the energy density of dark matter. So rather than thinking about WIMPs, let me think about a different paradigm for dark matter called asymmetric dark matter. Which is, well, let's think about this equality or this equation. So omega is the energy density. It's the size of the slice of that pie. So in units where everything adds up to 1. The energy density of atoms is the mass of the proton times the number density of protons or baryons. B for baryons, but protons and neutrons have roughly the same mass. So this is the equation I can use. And for dark matter, the same thing. It's the mass of the dark matter times the number density of the dark matter. Okay, so where do these numbers come from on the right side of these two equations? Well, the baryon number, the NB is the asymmetry between matter and antimatter. So it's the 10 billion and 1 versus 10 billion that I said a few minutes ago, that we know that's where it comes from. There has to be more matter than antimatter. That's what sets this NB. But we don't know what that is, so we call that baryogenesis, making of baryons. But that's just a name for something that we don't understand, and we just name it. And then the proton mass. Well, the proton mass, actually, we do understand what sets the mass of the proton, and it's controlled by the strong force, quantum chromodynamics. By the dynamics in QCD, set the mass of the proton, and I'll talk about a little bit more about how that works in a second. But then, so one idea that people have had is, what if, this is the idea of called asymmetric dark matter, what if dark matter, the amount of dark matter is set by, you have some dark matter and some anti-dark matter, and there's a tiny bit more dark matter than there is anti-dark matter, and in fact, the same mechanism that generates the baryon, or the matter versus antimatter asymmetry, generates the dark matter versus anti-dark matter asymmetry, and somehow it gets shared. And so if it's really literally the same physics, then you expect, at least at the order of magnitude level, the number density of the baryons to be equal to the number density of dark matter. Maybe there's some order 1 factors that your model predicts, but roughly these n should be the same. And so this is an old idea. Actually, the first paper that tried to do this is almost the same age as I am. And many people have worked on this recently as well. But if you so these kinds of ideas, they predict that the dark matter number density and the baryon number density are roughly the same, but they don't explain why the mass of the dark matter is approximately equal to the mass of the proton. So that's, you have not completely succeeded if you only explain why the two ends are equal. you also want to explain why the two M's are the same order of magnitude. And so you want a model that explains why M proton and M dark matter are roughly the same. Can we do that? Can we get both? And so if following that conclusion, well, if the mass of the proton is controlled by the strong force or quantum chromodynamics, then maybe there is some other strong force or copy of the strong force or dark strong force that sets the mass of the dark matter. Okay, so let me talk about the ordinary strong force. So the idea of the ordinary strong force is that it works like the electromagnetic force. You have this field strength alpha in electromagnetism, or the charge of the electron. You also have this parameter g or alpha in the strong force. But at different energies, this strength of the electromagnetic coupling or the charge of the quarks under the strong force changes at different energies. And unlike electromagnetism, it increases as the energy gets lower, and eventually it gets really, really strong. So you can't observe quarks by themselves. They get bound up into hadrons. But where this coupling gets very, very strong is roughly the mass of the proton, or the mass of all the QCD hadrons. But this mass is exponentially small. So this is the formula. It's exponentially small compared to the very high scale where you define your theory, where the theory behaves roughly like electromagnetism. And so this calculation and this explanation was done by Gross, Politzer, and Wilczek, and they got the Nobel Prize for this explanation. And so once this strength of the strong force blows up, it gets really strong. So once you're at this scale, lambda QCD, then you get these bound states of quarks. Quarks can't be free and they have to be bound. And you get a whole bunch of different bound states. So here's some examples in French, if you like. So the proton, the antiproton, the neutron, the lambda, the pion, the kaon, the mesons, b-mesons, charm mesons. Okay, so you don't have to know the details of what any of this means. But what's important for the purposes of this talk is that you get a dramatic array of lifetimes just from this QCD confinement idea. So the proton and the antiproton are stable. This is an experimental fact, but they don't have to be stable, right? Conservation of charge does not force them to be stable, and it turns out that they are. Protons do not decay, as far as we know. If they do decay, their lifetime is something like 10 to the 30 years or longer. So both the proton and the antiproton are completely stable. And this is because of what's called an accidental baryon number symmetry. Okay, but they're stable, that's fine. The neutron is very, very long-lived, so its lifetime is something like 10 minutes. But if you express 10 minutes in units of the mass of the neutron, then it's something like 10 to the minus 25 in those units. So it's extremely long-lived. And then you have these lambdas and these pions, which are quite long-lived. So in units of their own mass, they have very, very long lifetimes, but not nearly as long as the neutron. And then you have these things, which are short-lived. So in QCD, you just have this idea that quarks get bound up into bound states, but the bound states can have orders of magnitude different lifetimes, from infinity to very, very short. And so if you follow this idea that, well, maybe we should explain the dark matter in the same way we explain the proton, then you propose a dark QCD, and this was first done by this paper by Yang Bai and Pedro Schwaller in 2013. Just propose a copy of the strong force. So this is some gauge group, but the language doesn't matter. You have some new strong force. And then your dark matter is the dark baryon, or the analog of the proton in the dark sector, and its mass is some new parameter I'll call lambda, capital lambda, of dark QCD, as opposed to lambda QCD, which is a well-known parameter of the strong force. And then to get this to work, as I'll talk about in a second, you need a new field, which is heavy. So its mass has to be much larger than the mass of the dark proton, the dark matter, as well as the mass of the proton itself. And it also has to be bifundamental, meaning it has to carry strong force, strong color charge, and it has to carry dark color charge. And then, okay, here's a little technical point. You search for a model with a perturbative fixed point. So for the theorists in the audience, this is the running of the gauge coupling. But basically, the picture I showed before with the Nobel Prize page of Gross, Politzer, and Wilczek. So this red one is more or less the same picture. And then the blue one is the copy for dark matter. But they're, instead of in ordinary QCD where they're constantly rising, here they're flat for a little while, But then when there's this new particle, that causes them to stop being flat and start rising. And then you can predict the ratio of the mass of the dark matter, which is this vertical line, to the ratio of the mass of the proton, and that's factor of 3, 4, 5-ish, factor of a few. And you can also predict the ratio of the mass of the proton to this new particle, which carries strong force, and that's a factor of 1,000-ish. So here's an example parameter point from this paper. The mass of the dark matter is 3.5 GeV. So GeV is the units of the mass of the proton, roughly. And then the mass of this new particle is 870 GeV. And then why do you need this new particle? Well, you need it for two reasons. The first is to get the right mass for the dark matter, to get that the masses are equal. But you also need it for this asymmetry sharing idea, right? So that we know that there's some more dark matter than dark antimatter, and there's some more matter than antimatter. So these are called asymmetries. And we start with this field X, which is heavy, carrying some asymmetry. So there's more X than there is anti-X. And then the X can decay into ordinary matter and into dark matter, or ordinary quarks and dark quarks. And so every decay of the X shares its asymmetry. So you get the same the same asymmetry in quarks as you get in dark quarks. And so that means you get the number density of quarks today is equal to the number density of dark quarks today. And you predict that the mass of this X is about a TeV-ish, which is an important scale for the Large Hadron Collider. And then if this is your model of dark matter, so I'm not an expert on this and I won't talk about this for long, but dark matter is strongly self-interacting, right? We know baryons interact with one another. Of course, protons interact through the electromagnetic force, and there's no electromagnetic force for your dark matter, but they also interact if you scatter protons with one another. They have short-range interactions mediated by the strong force. That's something like the analog of the van der Waals force for the strong force. And so the dark matter behaves like a neutron. It has these short-range, very strong interactions. And the standard picture of dark matter actually has some problems, which have these fun names like cusp versus core, missing satellite, too big to fail. But if dark matter has this strong self-interaction that is short-range, potentially you can solve all of these problems. And so there's a nice review by Sean Tulin at York and his collaborator, Haibo Yu, which talks about this at great length. Okay, but here's the general picture that I want to talk about, which is that you have the QCD scale, QCD sector, which is all the normal stuff we know about, protons, neutrons, and all the other hadrons. And then we have the dark QCD scale, which is a dark QCD sector, which is a copy, but slightly heavier. So instead of 1 GeV, it's a few GeV, 3 or 5. And then you also have all the same hadrons, but the dark versions. And then you have this particle which can decay. Each X decays to a proton and a dark proton. So in the early universe, you have some X's. They populate the dark QCD and they populate the ordinary QCD. But then all the ordinary QCD particles, all the ordinary particles that are not baryons will decay back to the standard model. So all the things that in the standard model have very long lifetimes, or very short lifetimes, will also have very short lifetimes potentially in the dark sector, and they'll decay down to standard model stuff. All right, so let me stop there and ask if there are any questions, since it's sort of a natural breaking point.
Oh, there's one question in the chat.
Sure. How do I see that?
You can either pull it up or I can read it to you.
Sure, if you don't mind.
The question's from Emmett. Do you need some special feature of your interactions, some sort of magical conspiracy between the Yukawa couplings of your dark fermions and the dark QCD gauge couplings to produce the flat feature in the RG flow? You can tell this is a theorist asking the question.
I can tell this is a theorist question. And yes, you do need, I wouldn't call it some magical conspiracy. So this is called a pseudo Banks-Sachs fixed point. So you do need some, conspiring of the number of colors and the number of flavors to make this work, to make this approximately flat in the way that Banks and Sachs worked out, I think in the 80s or something like that. And so you do need to do that. So it doesn't work automatically, but for example, with 7 flavors and these two couplings with both of these gauge groups being SU3, then it does work out. So yeah, you need to have a bunch of flavors to get this pseudo Banks-Sachs fixed point. Yeah, good question.
If it's but if it's just a gauge coupling running, wouldn't you just expect for it to go to zero logarithmically?
Sorry.
I'm just curious about the flat feature.
Yeah, that's the Banks-Sachs fixed point, right? So you can you tune the one loop against the two loop beta function.
Okay.
By making the one loop unnaturally small by taking the coefficient of the one loop, which depends on the colors and flavors, and making that close to zero. Yeah, that's how that.
But then later on, like somewhere near the UV scale, it sort of tuning starts to disappear.
Well, so that tuning you only get a flat feature at a specific coupling, right?
Okay,
so the point of this picture is that regardless of what coupling you start at, you run towards that coupling, and then it's flat. And then once you integrate out this bifundamental field, you run away from that coupling towards confinement.
Okay, yeah. Thanks.
Yeah, so I didn't explain that in great detail, assuming my audience doesn't care, but I'm glad to hear somebody does care. All right, are there other questions?
Yeah, there's another question from Jean-François.
Yeah.
And yeah, Jean-François, feel free to unmute yourself if you want to clarify.
Yeah, so I figured out how to read these questions. So I said if the dark sector doesn't have electrodynamics, yeah. So in this minimal model, let's say, I've assumed that in the dark sector there is only QCD and no other forces, right? So that the dark quarks are only charged under this confining dark SU3, and there are no other forces there. Of course, that doesn't have to be that way, and you could imagine putting in a whole standard model prime, and I suspect if you're careful about how you engineer it, you could get all the right phenomenology. But for the minimal model, I'm considering, yeah, there's only dark QCD and no dark electroweak. Does that answer the question?
Yeah, but that means that if you have your dark neutrons and your dark protons, what's the difference then?
Yeah,
I guess if you've got seven, there's none. Okay.
There is none. That's correct.
I guess if you've got 7 flavors anyways, then it's all kind of it's a different zoo.
Yeah, that's right.
Okay, thanks.
So it's neutron in the sense that it doesn't carry, doesn't talk to a light photon. But yes, there's the neutron, there's the proton, there's a whole multiplet. They all behave roughly the same. If they're all degenerate, then really they're exactly the same and you don't care. If some are slightly heavier than the others, they'll all decay down to the lightest one, but that does not affect anything as far as I know.
I got one last question in a private chat. So why do we expect that the dark pion or the light short-lived states decay to standard model states?
I'll come back to that one. That's coming. Yeah, I have that calculation coming up. Yeah, good question. All right. Any other questions? Okay, so let me talk a little bit about the collider phenomenology. So I have this dark QCD. It has dark quarks. It has a confining scale on the order of 1 to 10-ish GeV. And then you have the stable dark proton or dark lightest baryon, if you like, which is your dark matter, and then the dark lightest meson, which decays down to the standard model, and then the whole zoo, which they typically decay down to one of these, either dark proton or dark pion. Okay, and then you have this heavy mediator. It's much heavier than the mass of the dark proton, and it interacts with both the ordinary QCD gluon and the dark gluon. Okay, so what happens when you produce this thing at colliders? Well, a nice analogy actually is thinking about an electron-positron collider. So and what happens when you produce quarks at an electron-positron collider? So the initial state here is not charged under standard model color, under the strong force, but you have this heavy mediator. It's much heavier than the mass of the quarks, called the Z boson, which interacts with both the initial state of electrons and this confining state of quarks. And so at for example, LEP, when you produce a very heavy Z and it decays to 2 quarks, well, you don't see 2 quarks because the quarks can't be free. And so the quarks turn into a spray of collimated particles, collimated hadrons. And so you see, instead of QQ bar, you see what's called 2 jets. And the jets are sprays of collimated hadrons with high energy, all going in roughly the same direction. So this one quark turns into this mess, and the other quark turns into this mess. But then there's more or less nothing in between, because the quarks, the spray of hadrons that comes from the quarks, all go roughly in the same direction as the initial quark. So this is the same thing as when you try to produce dark quarks at the LHC. You have this heavy mediator that you can produce because it has color. It has the same, it can interact with the protons. And then you have to pair produce dark quarks, but the dark quarks have to hadronize. And so you get this spray of dark hadrons, dark pions mostly, but they're collimated and they're all going roughly in the same direction. But they're invisible, right? They don't talk to the standard model in any significant way. So far it looks like I've just produced nothing. But then, as was asked, well, why do the dark pions decay to the standard model? And actually, this is a consequence of the asymmetry physics. So the asymmetry physics says I have to have this X, which can decay to a quark and a dark quark. But that means that I can draw this Feynman diagram where I start with a quark and an antiquark, and I have a T-channel exchange of the X, and I get a dark quark and a dark antiquark. I can also treat the X as just a point-like particle because it's much heavier, so I can integrate it out. And then because the dark pion is a bound state of dark quarks, this QQ bar can just be thought of as a dark pion. And so this is dark pion decaying to ordinary standard model quarks. And I can estimate the lifetime of the dark pion. And so this is the formula. Okay, fine, a bunch of parameters I don't really know. But the rough order of magnitude you expect is 10 centimeters. And if you remember the size of the Atlas detector, this is something like a few meters. It's much bigger than the size of a person, 10 meters maybe. But the resolution, the distance resolution of the Atlas detector is much less than 10 centimeters, actually. It's on the millimeter or less scale. So if this is my cartoon of the Atlas, it's actually a cartoon of CMS, but the idea is similar. A cartoon of the detector at the LHC, the rough length is roughly 1 meter. Of sort of the inner component, and the outer component is a few meters. And so if C tau is something like 10 centimeters, then this is the decay spray I should see, because not only are they produced, these dark pions are produced with large boosts. So most of them decay at distances much larger than 10 centimeters, but with a distance of a few meters. And so each one of these dark hadrons is going to decay back to the standard model. So the solid lines are standard model hadrons that can be detected at one of these experiments. And so this is why we've called it emerging jets. So at short distances, if I just look very close to the interaction point, there's nothing, there's no jet. And at long distances, once everything is decayed, it looks like an ordinary jet. It is very hard to tell the difference between this thing and an ordinary jet. And so as I travel away from the detector, the jet emerges. It turns from invisible to visible, but slowly, because of the exponential decay factor in quantum mechanics. Even if the proper lifetime is 10 centimeters, each one will decay quantum mechanically at a different place in the detector. And so you get all these so-called displaced vertices all over the detector. And so the strategy here, at least roughly the strategy we designed in our paper, is, well, you look for a jet, an ordinary jet, just like the kind we saw at LEP, except you look for a jet with very few particles inside the circle. So very few particles that are very close to the interaction point, and lots of particles that are far away from the interaction point. So let me say briefly, we have to simulate this. If you want to do any kind of analysis of a collider, you have to have Monte Carlo to simulate it. And so we have to simulate this weirdo dark QCD. It was partially in Pythia, which is the standard software to simulate dark QCD. But it was not really done well enough. So we had to modify Pythia to make the dark sector more realistic. And our code is now added to the standard release of Pythia, as long as you're using versions bigger than this number. So it's now there, but at the time we were working on this, it was not there, and we had to modify it. And so what does the event look like? Well, you start with 2 protons. You make 2 X's. X's carry strong coupling. They carry color, so you can pair produce them at a collider. And then one X decays to an ordinary quark and a dark quark, and the other X decays to the conjugate, the anti of that same state. And so your final state is 2 ordinary jets, like the kind you'd see at LEP, plus 2 of these emerging jets. And then the cross-section, well, the cross-section is smallish, actually. Depends on the mass of this X, but it's something like 10 femtobarns at the current running of the LHC. It's not very big. And so we did a study of, well, what would the discovery reach be? For example, if you look at the lifetime of the dark pion in millimeters, so C tau in millimeters, so 10, so 100 is sort of the expected number, but it can vary by, it can be much smaller or much bigger depending on if you vary the parameters. And then the mass of X, which sets both the amount of energy that the typical event has, and it also sets the event rate. So at higher energy, if the mass is too large, then the event rate is tiny. If the mass is too small, then you don't have enough energy to see anything. And so this is the estimate that we said with LHC data. Roughly 100 inverse femtobarns is roughly how much has been taken today. In the future, we'll sort of have 30 times more data. So we estimated that with more data, you can actually do quite a bit better, not in the lifetime parameter, but in the mass parameter, which is not so surprising because if you take more data, well, you're more sensitive to kinds of rare events. And then the question we had to answer at that time, at least, is, well, there's lots of cool papers from the LHC, in particular looking for lots of weird phenomenon. So could any of those have been sensitive to this signature that we showed comes from these dark matter models? And most of the papers from that time, so these are two of them, we're looking for what was called displaced dijet. So you have some invisible particle which travels for a while and then decays to two quarks. So it looks like this, right? You have a bunch of hadrons, but they all come from the same point. Maybe you have two of these displaced dijets. Well, an emerging jet is not the same, right? You have a bunch of different points where each one, some of the energy of the jet emanates from each of these little points. And so it turned out none of the searches at that time could have discovered this emerging jet. And so we were excited. We got excited about that. We got the experimentalists excited about that. And they went out and did this search. So in 2019, CMS published a search for an emerging jet and an ordinary jet. So this is the 2019 CMS search. Of course, you didn't read about this on the cover of the New York Times, so they didn't discover emerging jets, but they did the search and they set a limit. So it's interesting to see how exactly they did it. And they did roughly, I mean, a better, smarter version than what we proposed, but in spirit, the same idea. So the two variables that they looked at that they found had the most power was the average transverse impact parameter. So the impact parameter roughly is how far away from the origin does the energy emerge. And so on average, for QCD, it's like 0 or 10 to the minus 3 or something like that. While for these emerging jets, it's much larger. And similarly, you can do a momentum weighting of the energy. So how much energy emerged at large distances versus how much energy emerged at small distances. And again, for the standard model, it's near 0, while for these signal events, it's much larger. And they set a limit. So, and we can just compare to the limit we placed. The shape of the limit is roughly the same in the lifetime versus mass plane. And they thankfully use the same limits on these axes as we did roughly. And so it was very exciting when they did this and they set a very similar limit to the one that we projected that they would set with with their data. And so I went and read this paper and I looked and I see that they have several signal regions where they put different cuts on the different parameters. And I stared at this table for a long time and I noticed that signal region 2, they expect something like 32 plus or minus 5 or 6 events, and they observed 47. So I did a naive calculation, and then I went and asked my friend Ted, who worked on this analysis, and I asked a dumb theorist question: should I be excited about the 3 sigma excess in set 2? And Ted, who's an experimentalist and much smarter than I am, but he did say, good question, and we're going to repeat the analysis with 10 times more data, so we'll see what happens. So stay tuned. Probably is nothing, but could be very exciting with the next run. Atlas is also working on this, so there's a dedicated search at Atlas. So far, the only thing they've shown me is this simulated signal event, but it's pretty cool. You can see the emerging jet in these here, all the displaced vertices coming out of it. And this is a real simulated event, not the stupid thing that I drew with PowerPoint or Keynote that I showed a few slides ago. So it's pretty amazing. And the Carleton group is actually heavily involved in this Atlas dedicated search. And they tell me that there should be a result sometime soon. And so it's been a lot of fun working with my colleagues at Carleton who work on Atlas on trying to pursue this search and figuring out ways that Atlas can do better than CMS has already done. And then let me quickly mention LHCb, which is a different detector at the LHC, but it's much smaller. It has much smaller coverage, but it's better at doing particular things. And in particular, it has excellent tracking. So it can figure out where particles are with much better resolution than Atlas and CMS. And so this could have complementary discovery reach. So how much longer do you want me to take, Aaron?
7 or so minutes.
7 or so minutes. Excellent. Okay. Well, we'll do the lightning round extra lightning-y. So this is the stuff I'm working on today. So one thing is that there's work ongoing. So there's search. There's this workshop, the LHC LLP community. So LLP stands for long-lived particle. And there's this big effort between theorists and experimentalists to try to figure out what are all the ways that the LHC can search for long-lived particles. This is the 7th workshop, happened earlier this year. And there's a lot of work associated with snowmass going on in the US. And this working group produced this 301-page paper that you can find on the archive from last year. And there's a chapter on dark showers, right? Which is showering is what we call it when in QCD, a quark turns into many hadrons. So we can think about dark showers in this way. And so this is the chapter on dark showers in that 300-page report that I worked on. So if you're interested in our model plus several other kinds of models and motivations that can provide this kind of physics, have a look at that. There are also other detectors that are being proposed to look for long-lived particles specifically. So here's a list of 6 different detectors. The Methuselah detector is one with significant Canadian collaboration, in particular at Toronto and Triumph, I think, but possibly other places as well. And then this phaser detector is actually funded. So it is going to be built in the next few years. And these all are further away from the collision point than Atlas and CMS. And so they can look for particles with somewhat longer lifetimes than Atlas and CMS can, particularly of these kinds of physics. Okay, and then trigger strategies. So, so this is the slide I want. So at the LHC, the event rate, how often the protons collide is something like 40 megahertz. And since these are very complicated detectors, that's a really ridiculous quantity of data. And so they just cannot record it all. And so they have to trigger on events that are interesting. They have to find interesting events, throw away all the rest, and get the data rate down to 100 hertz. And so in this plot, the reason actually it cuts off at 400 GeV is not because the events are uninteresting or because it would have been discovered by a previous experiment. It's just because it's very hard to trigger. The triggers typically do not work at energies lower than 400 GeV. So what I'm currently thinking about is what can you do if the energy of the emerging jets is somewhat lower? And one thing we can do is, and this is work with my graduate student Dylan Linthorne, is try to just count. So you have this detector and it can read out very fast, and for a trigger it has to read out very fast. What if you just count the number of hits? You just do some geometric pattern matching and maybe even use fancy machine learning algorithms to do this geometric pattern matching. And so this maybe can be done, and you can use it to make sure that the lower energy emerging jets get triggered on and they're not lost in this trigger. We can also think about flavor. So this, there are 3 copies of the standard model quarks that could in principle interact with these dark quarks. And if you can do quantum mechanics, you can see that these quarks and these new particles can lead to weird flavor changing effects. So kaon mixing and things that in the standard model are very well understood. And so if you have new physics contributing to that, then it could be excluded. And so we're studying how that works. And this is work in progress with a postdoc in my group, Wafia Salem. You could also ask, well, you now have this extra SU3 force in addition to the other standard model forces. Can this be embedded in some bigger group? And so you have unification of all the forces, not just the forces in the standard model. And so we came up with a way to do this. That's work in progress. And the gauge group is SU3 to the fourth, which we called quadrification, because there's this idea of SU3 cubed in the standard model called trinification. And this idea automatically gives you the fields that you need to generate the asymmetry. So this is work in progress with former student Ben Wilkinson-Zahn. And so you do get gauge coupling unification. Everything runs to a point. Okay, so let me conclude the physics, and then I'll talk about one more thing, which is, so these asymmetric dark matter models are interesting and important, especially now that we all these years of searching, we haven't found any WIMPs. And they naturally give rise to these emerging jets phenomenology at colliders, which are novel, motivated, and we've started this program. The LHC has started a program to search for these things. And so the strategies we've talked about, the strategies we worked on, can reach very low cross sections and be sensitive to a broad range of a broad class of models. And really, this is part of a broader class of theories that the LHC and future planned experiments are only beginning to explore. And so there's lots of interesting work to do, both in terms of the bottom-up perspective of thinking of phenomenology at different experiments, and in top-down thinking about the flavor structure and unification of these kinds of models. Okay, so let me take 2 minutes to give a pitch. So we are looking for grad students at Carleton. So if you are thinking about applying to grad school, or if you know someone who's thinking of applying to grad school, they should certainly consider Carleton. So we have world-class research in particle physics and in medical physics. So in particle physics, there's people like me doing particle theory, and we have the biggest phenomenology group in Canada. So phenomenology is people doing theoretical work, but connected to experiments and trying to make predictions to experiments. There's a world-class group of this at Queen's, but you should certainly consider Carleton as well. There's experimental work on both of the experiments that I talked about. So Atlas and Deep, there's people working on at Carleton, as well as various other cutting-edge projects. And then in medical physics, we have medical imaging, radiation therapy, and radiobiology. So Carleton is a great place. We have MSc and PhD positions in all three of those areas, so in theory and particle experiments, and in medical physics. So please visit our website, and if you have any questions, please feel free to contact me anytime about grad school at Carleton or about any of the physics that I talked about today. Thank you. Thanks, Aaron.
Feel free to clap virtually or unmute and clap if you'd like. Thanks for a really nice talk. I really enjoyed that. That was a presentation. So, and you took that 7 minutes I gave you extremely seriously. That's the first time that's ever happened to me.
Yeah, I have a clock on my computer that, yeah.
So yeah, so we definitely have time for questions. You can either raise your hand in the participant list, you can scream out, unmute yourself and talk, or ask a question in the chat. There's a question from Joe.
Hi, Daniel. Great talk. Very, very nice. I was wondering, with respect to targeting these lower energy emerging jets, whether you'd considered or looked into these CMS data releases where they don't do any sort of triggering and they just sort of, scout or, yeah. So there are different levels with that. I think they're experimenting with. Have you looked into that at all?
Yeah, great question. Considered yes, but looked into no. Yes, I mean, I think it would be a cool thing to do, but I have not actually attempted it. From talking to people who have tried to do analyses with these open data, it's you have to more or less commit 2 years of your life or 2 years of your student or postdoc's life, which at the moment I don't have 2 spare postdoc years or student years to spare. But if one of you comes to Carleton or 5 of you come to Carleton, maybe we can make it work. I think it is very interesting and worth doing, but I have not yet tried to do it.
Well, but there's no technical impediment to using CMS detectors to look for these sorts of emerging jets. It's,
Yeah, absolutely. I mean, the CMS detector has put out the first limit, right?
Oh, right. Yeah.
So for sure, the CMS detector should be good at it. There's complementarity between all the detectors. They're going to be good in different regions of lifetime space, but they all should have some discovery reach. The rate is low, so I mean, I don't know what exactly is in these CMS open data. If it's only some, pre-scaled min-bias trigger things, then you're not going to see it. You have to be sensitive to sort of femtobarn level cross sections. But yeah, it's worth investigating more for sure.
Thank you.
There's a question from Tony.
Yeah, actually, I was going to say, I suspect that's mostly minimum bias data, and I don't see how you could extract anything from that. You got into the trigger at the end. I think that's going to be absolutely essential to develop a trigger that's somewhat sensitive. And I don't know what appetite there is. These are 3,000 collaborators, and whether this has captured enough attention of enough of the collaboration that they would consider a trigger modification to bring this in. It's always a big problem. And then I guess the other thing that struck me was collecting more data. The luminosity just goes up and up. The number of protons per beam crossing is increasing. The pileup must be getting worse and worse. And I really was struggling to see how you could deal with the pileup and know for sure that you would actually get clean signals with no events at the center.
Yeah, so for sure. So the
Oh, and I was going to comment on your last two slides of attempting to coach our students. You already stole Liz Fletcher, so that's enough.
Very good. I don't know Liz, but yes, if she's tuned in, I hope welcome to Carleton, and I'm sure she'll do great. Yes, I'm sorry that I'm sure you guys also want a bunch of students, so sorry.
Yeah, we'll be on we'll be poaching as well. No worries.
Exactly. We're happy to give you guys audience with our students to come poach. Absolutely. So in terms of the trigger, get more slides here. Yeah, so you can just, if you're in the MX of that one TV kind of regime, you can just use an ordinary HT trigger or 2-jet trigger. Any of those will work. And the CMS analysis did that and it worked fine. But so if you're over here, the rate is much higher, but the triggering is much harder. Min bias triggering certainly never gonna work. You need something a little bit better. So there are some people who have expressed interest in doing something like this, doing some fancy triggering for run 3, run 4.
Some of your events, if the count was 0 in layer 1 and 2, that would be exactly what you're looking for, right? Or even further.
That's right. So that was what we proposed. That was our dumb theorist proposal, is saying the count will be 0 in layer 1 and 2. But the experimentalists were smarter than that, and so they did this PT weighting idea, right? You count the momentum fraction. So pileup is soft, and so it's the contribution to the PT weighting is actually going to be relatively small for pileup. And the other thing about pileup is that it's isotropic. So even if you have a lot of pileup, if you have a relatively narrow cone of your jet, that already eliminates a bunch of it. And so these guys showed very convincingly that it's not at all a problem. Today, at high luminosity LHC, certainly you have to think harder. But all the people working on this who I've talked to seem to think that it's not a killer, at least for relatively high mass emerging jets.
Cool. Very nice. Thank you.
We have time for more questions. I know I'm supposed to count to 7 after saying that.
Is that right? I've never heard that rule of thumb.
Just long enough that it becomes awkward for everyone.
So what would be your elevator pitch for Methuselah?
For Methuselah. Yes, I mean, my elevator pitch is that it's hundreds of meters from the interaction point, and so you can see things with lifetimes of hundreds of meters, which you cannot see at CMS and Atlas. That is not. I would say that's an elevator pitch for sort of all of these experiments. So it's not an elevator pitch that distinguishes any of these experiments. And I have not actually studied carefully. That is on my list of, on my to-do list of like, you know, what is the difference in physics reach in all of these things. But yeah, all of these experiments sort of have that, you know, there could be new physics out there with lifetimes significantly longer than the size of Atlas. And you want to discover them because you're making them at LHC anyway. And so that is my elevator pitch.
Well, but do you need to have, you know, 4 pi coverage of the interaction at a distance of 100 meters, or can you put a detector on the surface, for example?
Well, that's what Methuselah is, right? It's not 4 pi coverage, it's a detector on the surface. It's big, but it's certainly not 4 pi. I think, yeah, I don't remember off the top of my head what the angular opening angle of Methuselah is, but it's none of these are 4 pi.
Right.
There's another question from Amit in the chat.
Sure, let me see. See if I can see it. So to anticipate any interesting consequences on models for electroweak symmetry breaking, cosmologically. Yeah, so I don't immediately see any consequence in those two models in particular. So the breaking steps are sort of, they're all at very high energy in this QCD plus standard model. But let me answer that question slightly obliquely, which is that there's also these kinds of models, the so-called neutral naturalness model, which solve the gauge hierarchy problem. So we know that this loop in the standard model is a problem, and it makes the Higgs very sensitive to very high scale. And you can solve this problem by putting in new states. And so this is the supersymmetry or composite Higgs solution, is new scalars or new fermions. And in supersymmetry or composite Higgs, those things have color, but they don't have to have color. They can have dark color. And so this is the idea of twin Higgs or folded SUSY or neutral naturalist. You need a color force. It doesn't have to be the standard model color force to solve the hierarchy problem. And so when you do this, you get this dark QCD, and actually you get almost the exact same phenomenology in these kinds of models as you do in what I was talking about, except that the mediator is not some bifundamental, it's the Higgs itself. And so that also motivates looking for these lower energy emerging jets where the energy is 125 GeV or something like that.
But does that set your couplings though? Because
Sorry,
to
say that again?
cancel these, would that set your dock QCD couplings?
It does.
Like if you want, yeah.
But it turns out about the same. It turns out you get a confining scale of a factor of a few larger than standard model QCD.
It's interesting.
So we've just hit 3:30. I suggest that we virtually applaud and thank Daniel again.
Thank you. Yeah, thank you so much for having me. This was fun.
So if you don't mind staying around for
Sure.
another 5 minutes or so in case there are other questions,
Happy to do that.
that would be great. But otherwise, I guess we can end the recording and let everyone who needs to go.